So DES. So it stands for Data Encryption Standard. So it is, of course, here we saw last time symmetric and asymmetric algorithm. We're gonna see two symmetric key algorithms or ciphers and one asymmetric algorithm. So published multinational by the NIST. So it's dates from long time ago. So basically, I think it started. The development of this algorithm started in 1973. In 1975, they published the standard and the details, and then I think the mainstream use started in like 78 or 79. Okay. But it's also dates really no interesting for, with respect to the history of computer science, etc. It's considered very old algorithm, but it is still adopted. Now, this is how it works. Basically, when you want to encrypt data with DES, you need to split the data into 64 bits blocks. Okay, so you split the data into blocks of size 64 bits. Okay, and then you encrypt every 64 bits separately. Okay, so basically the DES cipher. It takes as input 64 bits of plain text, and also it takes as input a 56-bit key, and it will generate 64-bit ciphertext. Okay, the decryption side very simple. Okay, it will take as input 64-bit of ciphertext, a key of 56 bits, and it will give you the 64-bit plain text. Okay, so. The encryption process is made of two permutations, Vboxes, which we call initial and final permutations, and 16 fiscal rounds. So what you do, first of all, you do one initial permutation, you're gonna see it, then 16 rounds of a certain function, then you finish by a final permutation. Okay. So basically, this is the model. So one first initial permutation, then 16 rounds of a certain function, you're gonna see it. Okay, and you end up with the final permutation. So in the 16 rounds, every round requires one key of size 54 bits. Now, while the key for a single DES is 56 bits, so basically you need another component here, which is the key generation or round key. Basically, it's a key extraction, kind of key extraction. So starting from those 56 bits key, you will generate 16 48 bits keys. Okay. Yeah. So we're gonna see all the what is in there in every of these boxes, one by one. So basically, after this lecture, if even you want to implement DES, you can implement. Okay, you can implement. Because you will see, you will have all the choices to do that. And you need to understand these transformations because it's typical that in quizzes or in exam I ask about this. Okay, I give you something in input to tell me what is the output. Okay. So permutation, basically, you have 64 bits. You will replace them. You will permutate them in. Using a particular model. Okay. So for example, bit 2 you put it in position 23. Bit 54 you put it in position 7. That's it. So basically, the bit 1. This is the initial permutation. Bit 1. It goes to. It becomes bit 40. Okay. So in the output of the permutation. For bit 40, for you take the bit 1 of the input and you put it there. So it's you permutate all the bits, and in the final permutation the same thing. Okay, so this is a simple permutation. You don't reduce the number of bits. You don't increment it. Just you replace them. So input 64 bits, output 64 bits. Okay. So yes.
And the final permutation we switch the
no.
Because you can see here, just quite the opposite of what we have in the initial. 1 was going to 40, now 40 going to 1.
It seems to me it's
This is
so here.
a coincidence, I think.
No. So see here, the point is, when you use the encryption algorithm, you should think about the decryption algorithm from the other side. So, because you can come up with a very complex transformation algorithm or encryption algorithm, but what if, if it is not kind of reversible in the decryption side, it's useless. Okay, so it's the first time I see it here because it's not, I don't think it's by chance. So it seems it's the opposite. So exactly the opposite. So if they choose to do that, because in order to make the decryption side 100% reversible, of course. But if you start from cipher text, you obtain the initial plain text. Okay. So this is the initial permutation. Initial and final permutation. These permutation tables are known, are fixed. Okay, so you go to the DES standard and you will find the same thing. So basically, as it seems, it's so if you take 25 basically this is 1. 25, 8 times, yeah, this one, 64, yeah. So it's opposite. So you do the opposite process. I noticed.
It doesn't make sense, right? Because this is only the encryption, it's not the decryption. So if you mix them up, then repeat them in just the encryption, they will go back to their original place. Why would you do that? It doesn't make sense.
Why they make it kind of symmetric?
No, you didn't do nothing in this case if you are mixing them and then putting them in the
Why?
same.
Unless the rounds are changing.
Yeah, here assume, of course, you do the initial permutation, then you do the 16 rounds of Fistel ciphers. You're not applying them one another. Of course, if you do initial permutation, then just after it you do the final permutation, end up with the same thing. But here, no.
No, what I mean is, if we take these stages away,
Yeah,
the
okay.
first one and the last one,
Okay.
you'll end up with the same thing.
It's part of the
Yes.
algorithm process.
Not really.
Yes, because you change the positions, then you put their positions back.
He's right.
So everything is 16 round actually.
So basically, if you don't do the initial permutation, so bits will be in a certain position. Then after the 16 rounds, you do the
It will not be the same.
Not too much.
The question is,
Why? I think it would.
We can do an experiment.
Okay.
Very simple.
No, it's not simple.
I think
It's not simple.
16 round. It's the bits are different.
Here, see. You will apply the 16. What you are talking about? You will apply the 16 rounds on the bits before permutation,
Yes.
and this is the first case. So basically, if we don't use initial permutation, now the other case is you apply the 16 rounds after doing the permutation.
Yes.
So basically, having changed the bits. It's not going to be the same. No.
Because you only change the.
Because the point here, the input of the 16 rounds will be completely different. See the point? So it's not like when you do the final permutation, you will take back
the change depends on the position too in the 16 rounds.
Yes, but the bits will be will not be the same. Okay. So I don't know.
It's crumbled.
Yeah. So there is an initial step that will make the data different. The input data for the 16 round will be different. Okay. So who took 454?
I took it when I forgot.
Okay, but here this is in 454 normally you cover why the why of the things.
Yes.
Yeah, basically why these permutations, why it is here reversible. Personally, I'm not a a cryptographic expert. I cannot tell you. Okay, but I am interested by the implementation side, how this is implemented, and some properties. Okay, the why I can't tell you why exactly. So yeah, this is a simple example of the transformation of the permutation. So this is the data, 64 bits as input, and if you apply the initial permutation, so basically here it seems that only 2 bits, all the bits are 0 except 2 bits, number 25 and number 64. So I think bit 25, which is 1, in the initial permutation, it becomes 1. So bit 25, basically, you look for 25, it is where? 25. So basically, where we put bit 25? So 64.
Fourth row, first column.
Where is 25? It's here. Okay, so you take a bit 25, and in the output it should be in this position. In the output it should be in this position. Okay. So this is basically position here 32, 33, 34, 35, 36, 37 normally, right? Yeah, normally 37. So here, the algebras are 0, and the final permutation, bit 25 becomes bit 64, and 63 becomes, this is confusing. So here, this is, again, bit 25, right? So you take bit 25, this is 1, and in the output, bit 25 becomes in position
64.
Hmm?
We can see fourth row, first column.
We're talking about the initial permutation. So
You count from the top from 0, 1, 2, 3 bits.
Yeah, I know. This is 8. This is 8. This is 8. So this is basically bit 33. Okay, 33, 34, 35, 36, 37. Right. So bit 37 in the output should be bit 25 of the input. Right. This is what it means. Okay. And 25 in the input is 1.
64.
Hmm?
64.
What? Here, 25. This is 25 in the input.
That's all changes. It will be changed to a new position.
Yeah. 25 now it is in position 37.
Yes.
You see. So normally, with I think there is typos here. By the way, the book for Luzan, you are aware it contains a lot of typos. Okay, I should send you the list of typos. Yeah. So here, as I understand, this is basically here. It's doing the opposite. I think final permutation. In the final permutation. Yeah, the final permutation makes sense. Yeah. It's the opposite basically. It's doing the
This is
opposite.
what we.
Yeah, it's straightforward. So, yeah. And let's move on with so initial permutation. This is the easy part. Now the rounds, the 16 rounds inside. DS uses 16 rounds. Each round of DS is a phase 2 cipher. So what we do in in every round, you take the 64 bits data as input, you split it into 2 parts, 32 bits, and then you apply. You take the first of the right side or right 32 bits, and you use them in this function along with the round key. The round key. Okay. So basically, the size of the key here will be what? 48 bits. Okay, 48 bits. So basically here, you take the right part, use it in the function along with the key. You get some result here, 32 bits also. What you do, you will. This plus is what?
Bitwise.
This is XOR. XOR operation. XOR bit operation. So you XOR it with the left part of the input. Then you will switch. So this part you will put it at the right, and the right part you will just put it here without any modification. So basically, in every round you are touching, you are only modifying the right part. The left part is the previous round right part. Okay. Okay. So okay, here XORing or whitening, it's easy. Now the core is here. The core is in the function. We're gonna see what happens in that function. So this is what happens in the function. So basically, always think about the input and output. So basically, as input, you have 32 bits and the 48 bits of the key. This is the input. Okay. So what we do? The first transformation is an expansion. Vbox expansion. What does it mean?
I mean 32 plus
You expand. So the data is 32 bits. You make it a little bit larger. According to you, yes, here it's written. But since the next step is XORing with the 48 bits of the key, so the expansion should give you 48 bits. Because when you XOR two sets of bits, they should have the same size. Okay, they should have the same size. So you expand those 32 bits into 48 bits. We're gonna see how. Then XOR. Then it goes through switch boxes. Okay. Then or S boxes, and then you go to straight Vbox, which is again a permutation. Okay. So let's start the expansion box. How it is done? How you expand? Because when you expand, you will add bits.
Yes.
You will add bits. Okay. So this is how it's done. So basically, you have 32 bits. So 8 blocks of 4 bits each. Every 4 bits becomes 6 bits. How? You will take the first bit of the next block. So basically, you have the same 4 bits here, and then for the 6th bit, you take the first bit of the next block and you put it there. Okay. And the same here for this block. The first bit of the six bits will be the last bit of the previous block. Okay. And here the point is this one comes from where?
The last.
This is the last block of the last bit of the last block, number 32. Okay, you put it here. So you kind of expand it this way. Straightforward. This is straightforward. So you take 32 bits, you return 48 bits. Yeah. So this is the expansion Vbox represented as a matrix. Okay. So 1, 2, 3, 4. Then here, this is bit 5, and here you're gonna have bit 4. Okay. And 5, 6, 7, etc. Clear for this Vbox? Expansion box?
No. You don't have a value in the first bit and the last bit. What is the value?
You see it's written here. So basically for this one, you take the last bit of the last block. It's circular.
Before the last. The black one.
And when I say the last, this one. This one.
Oh, yes.
The last bit of the
original
input. Initially. Okay, so this is the expansion box. Now the XORing sometimes is called whitening. So after the expansion permutation, DS uses the XOR operation on the expanded right section, the round key. Yeah, so this is the step. This XORing is the only step where the key is involved. Other than that, the key is not involved. Just in the XOR of the fiscal function. Okay. Now the core. This is the most the heart of DS is the S boxes. Okay. This is the heart. So and basically it takes 48 bits and returns 32 bits. So the S boxes do the real mixing of the confusion. DES uses 8 S boxes, each with a 6-bit input and a 4-bit output. So here it's the opposite of expansion. So you're reducing. You take 48 bits, you return 32 bits. Okay. So how it works? So of course you split the data into 8 parts, okay, 8 blocks, and every 6 bits will give you 4 bits. How this is done? Using this scheme, basically you take those 6 bits you split them into two parts. The 4 middle bits and the 2 external bits. Okay. So the 4, by the way, it's not the original. Oh, it's not the original. Okay. Because basically we went through, because you say this is the opposite of the expansion, right? No, because we XOR them. We went through the XOR, so it's completely reshuffled. The data is completely reshuffled. Okay. So what we do, we use the 4 middle bits to count to generate a number. Okay, and these 2 external bits to generate another number. So these 2 numbers will be used to access a cell in a certain matrix, which is the S box basically. Okay. So basically here, this number is the row, the index of the row, and this green number is the index of the the index of the column, and this will be used as the index of the row. Okay. So here, of course, when you have a matrix, it's a matrix filled with numbers, and the numbers here. So basically, it's a 16 by 4, which gives you how much?
64.
64 possible values, and 64 values it requires how many bits?
6.
6 bits, yes. 6 bits. Yeah, 6 bits. Yeah. But the number you will find here is can be represented by 4 bits. Okay, by 4 bits. So basically, this is the numbers there. So basically, with 4 bits, you can represent number from 1 to 16, or 0 to 15. Okay. So this is the S box. This is S box 1, and you have 8 different S boxes. 8 different, because you have for every block a separate S box. So here it works well with an example. So suppose the input of the S box 1 is 100011. So what is the output? So basically here 1 and 1.
Row 3.
You split the number into 4 middle bits and the 2 external ones. The middle ones will give you what?
The column.
1.
So that's 1.
The second.
Column.
This is basically the column. So this is, we are talking about column 1. It might be 0. So it's the second column. And the 2 external bits will give you
The last.
3. 3. Okay. So basically here, if we go back here, so what is the number here?
12.
So basically we said column 1 and line 3. So this is 12. You take 12, you represent it in binary, it will give you 4 bits, and this is the output. Okay. So basically here, this is what it said. So this is binary, which is, we look at the value in row 3, column 1. The result is 12 in decimal, which is binary 110. So the input of 100011 yields the output 110. 1100.
The numbers in the switch boxes is random.
The S boxes are the permutation box is known.
No, that's what.
Yeah, it's known. It's known. All this because of compatibility issues for the, remember, Kirchhoff principle. The system is known. The algorithm, everybody knows it. Okay. The problem is the key. Okay. Now this is the S box. Again, it is the core of the algorithm. The last step is straight permutation. In the straight permutation, you take as input 32 bits, you return 32 bits, just replacing them, permutating them. Okay. So this is the permutation. Okay. Yeah, so it's a simple permutation. Okay. Now this is the big picture of DES. Initial permutation, then round 1, again, remember that we take the right part, we use it in the fiscal function, we XOR it with the left part, and then we put all that in the left side of the output, okay? and on the right side of the output, etc. You keep repeating that 16 times, and in the decryption process, you will reverse. So basically, you start from the bottom. Okay, you start from the bottom, and you do use the 16th key as the first one. Okay, and you do the reverse process until you get back to the plain text data.
So you have one big key, but you use it in 16 different ways by choosing one bit.
Yeah, the one big key is used to generate 16 other keys. Okay, we're gonna see this is the algorithm. This is the algorithm for key generation. So you start by 64 bits. Typically in we set the key for DES is what? We said 56. But in practice, we supply a key of size 64 bits. So there is a first step which will reduce that to 56 bits. Basically, it is parity drop. What is parity drop? What is parity drop?
The noise bits, you take them off.
So which are? So basically,
That's
64 to get 56, you need to get rid of 8 bits. What are those bits?
You take 8, you go 8 and take 1.
The last bit of every byte.
Yes.
The last bit. So bit 8 will not be there. Bit 16, bit 24, bit 32, etc. All these will go. This is what we by which we mean parity drop. Okay. So the parity drop. This is the parity drop. So basically, as you see here, and you do also some kind of permutation, not very random, but so you notice here that bit 8 you can find. There is no bit 8. Bit 16 you will not find it. 24, 32, all these you will not find. Okay, because they are removed to obtain 56 bits. Okay. Now if we go back here, then we do for every round, or to generate the key of every round, we do a shift. So it's a left shift. What is a shift?
Just a question to the...
Yes, to move the bits either on the right or the left. So here the left shift. But when you shift, you need for how much you shift. What is the degree of shifting? Okay. So and degree of shifting is specified here. It's also known. So number of bits shifts in every round. It depends on the round. So for round 1, you shift just one position to the left. For round 2, one position. Round 3, 2 positions. 4, 5, 6, 7, etc. 4 positions, 2 positions, and then 9, 1 position, etc. Okay. So this is the amount of shift which is done in every shift. Okay. So for example here, those shifts. This is how many positions? Because this is round 1. 1. Round 2, the same thing. 1. Probably around 5 and 6 will be 2 positions. Okay. So these are the it says. So 1, 2, 9, 16, 1 bits. All the others are 2. Yes.
Can we go to the previous tab?
This
These
one?
numbers represent the bit number.
Yeah, bit number.
And because you said you will not find 18 and
No, 8. 8, 16, 24, etc. Because it's called parity drop, parity bit drop. Okay, always when you have a byte, 8 bits, the last bit is called the parity bit. For example, if you need to represent a negative number in a negative number, basically use the last bit to specify whether it's negative or positive. This is why I call parity bit. Okay. And then I think here the next step is compression Vbox. So the compression Vbox, again, as input, every round of the key generation takes as input 56 bits and return 48 bits. So there should be some kind of compression. The opposite of expansion is compression. Okay. So we compress those 56 bits into 48 bits, and the compression Vbox is simply a table. See here the shape, when you see it like this, it is compression. When it's the opposite, it is expansion. Okay. So Yeah, this is the key compression table. Again, here it is playing with the parity bits. Right? So from 56 to move down to 48 bits, you remove the parity bits. Right? You don't see 8, you don't see 16, you don't see 24, 52, etc. So, so in total here we have 1, 2, 3, 4, 5, 6 by 8. These are 48 bits. So, basically these are all the details of the ES. Okay, if I ask you, it happened on some old semester. I was not the instructor, but the project, there was just one project. The project was to implement the ES. Okay. So you can, if I ask you this, you can. Would you like to do it? No. It's useless. As I say, it is useless. You know the algorithm, you know how to write it, and you don't see any benefit of doing that.
Maybe in cryptography cells.
No, حتى cryptography يعني implementing is just implementation. So because you know everything, it's just
if you implement it, you would really appreciate
right. Yeah, you can see this. So two desired properties. When we assess how secure, how good is an algorithm, cryptographic algorithm, in particular symmetric key cryptographic algorithm, we have a couple of properties we need to consider. And for symmetric key cryptography, avalanche effect and completeness. Okay. So avalanche effect we mentioned last time. So avalanche effect is if the plain text data, the input data changes a little bit. So for example, 1 bit changes, you need to see that it has an avalanche effect. You know what is an avalanche? Okay, in the snow, etc. When you have something starts very small and then with time it becomes very big, very large, very big. So because an avalanche can be triggered by a small stone and then it becomes a huge hurricane. So here, to check the avalanche effect, let us detect 2 plain text blocks with the same key that differ only in 1 bit. So basically, you take one example. This is your plain text data, 0. Okay. Then you apply key, use the key to encrypt this using the ES. So you obtain this output. It is in what here? In which format? Hexadecimal. So they represent 64 bits. Okay. Now, this is the result of compressing, of encrypting this data with that key. Now, what do we do in the second experiment? We change just 1 bit of that plain text data, and we repeat the same process using the same key. And see here what we obtain. Another completely different data. And if we basically what we do in this experiment, we compare the bits, because here you don't see really the bits. You see just hexadecimal. You cannot tell. If you compare the bits 1 by 1, so whenever there is a difference, for example, beta position 1, beta position 2, etc., whenever there is a difference, you increment certain counter. So basically, we found what? We found that although the 2 plain text blocks differ only in the rightmost bit, the cipher text blocks differ in 29 bits. So, no, in this example. So basically, out of 64 bits, 29 of them changed. Okay, so almost the half of them changed. Okay, so here this means that changing approximately 1.5% of the data, plain text data, results in approximately 45% of data changed in the ciphertext. Okay, so is it good?
Yes, it's excellent.
It's perfect because again, as we said last time. If all the bits change,
you can just flip them.
Yeah, that's a big problem because by just flipping them you get the initial data, okay, or the same result as the first experiment. If nothing changed, also it's a problem. Okay, so the best trade-off would be in the middle, somewhere in the middle. Okay, so this is an example of how it works. Basically, since the DES uses 16 rounds. here in the experiment, they will follow the data while it changes from round to round. So basically, after one round, only one bit changed. After 2 rounds, 6 bits changed. After 3 rounds, 20 bits changed, etc. So let's say 29, 30. Then keep switching between around 30. Okay, which is fine. Okay. So this here you see also the need for several rounds. Why 16? Why 16? Why not 1 or 2? Okay, because it seems there are a lot of transformation. One looks enough, but see here after one round, only one bit changes, so it's not enough. Okay. The completeness. Now the completeness effect means that each bit of the ciphertext needs to depend on many bits on the plain text. So at the end, they are quite related. I've mentioned the completeness. So basically, the 1 bit of the output result should depend on almost all the bits of the of the input bits. Okay, this is the completeness, and for both DS satisfies those nice properties. Okay, so DS criticism, of course, DS has been criticized for during this how much now 40 years, right? Almost 40 years of existence. Too long. So let's say involvement in DES design was criticized. So basically, some say, I heard it a lot, the NIST or the NSA, what's the NSA?
National Security.
Yeah, National Security Agency, okay, of US. So they claim that they made it deliberately weaker, 56 bit keys, so that they can break it.
Because at that time, 56 was impossible to break.
Yeah. So yeah, but as it seems, if we believe these claims, they knew how to decrypt it from day one. This is why they kept using it. Okay. Yeah. So idea is that the NSA made this easy for them to break, but not everyone else. So the problem here is in the key size. So 2 to the power 56. Possible keys is not large enough. So, there were several attempts to break DES, and some of them were successful. Okay. So in the 70s, they published a design of $20 million machine to break DES in a day. This is back to 70s. Yeah. But remember, when DES is used in these days algorithms, the key keeps changing very frequently. Okay, it will not stay for a day. Okay, but the problem is if you capture one packet, okay, and then you spend all the day decrypting it, you will break it with just 56 bits. Okay. So yeah, other attempts like in '98 Deep Crack, it's a cracker for $250,000, etc. Yeah. So this is why there is a better version which has been proposed, which is the triple DES. So again, the major problem of DES, or the major criticism, is the size of the key. So the idea is to basically apply DES in a loop 3 times. No. Okay. And for every iteration, you use a different key. So in total, you will have larger. Okay. So here the process is to start by encrypting the data, the data with a certain key. Wait a minute. No. You start here. Okay. So you encrypt the data with a certain key. Then you decrypt it with a second key. The result, of course. You take the result, you decrypt it with a certain key, and then you take the result and you encrypt it with a third key to obtain the cipher. Okay, so the length of the key is 168 bits, but here they say effective key length is 112 bits. Here there is an idea of an attack called meet in the middle attack for this, but still you need to guess the right key, and still too slow for brute force. Yeah. So there are a couple of weaknesses, but it is quite secure. So brute forcing will take forever. So yeah, this is how. But here I think there is a typo. I think this one is key 3.
Yeah.
This chooses 3 keys. Okay. Again, another side typo. Now triple DS is now very commonly studied. So I think since made part of DS in 1999. So since like 2000, DS is not used as single DS. So we use triple DS. And in typical protocols, secure protocol like SSH, SSL, etc., they triple DS is the one which is used. So basically, yeah. So at that time, government organizations using DS are encouraged to convert to 3DS. And then the 2 major standards for symmetric key cryptography still are 3DS and AES. Okay, so yeah, DES by itself it's not supported anymore. Okay, but 3DS is still there. Okay, with AES algorithm, which we're gonna see next time, are the major standards for symmetric key cryptography. There are other like RC4, like other symmetric key algorithms, but these 2 are the major ones. Okay.